Hi guys, welcome to 13.4, Center of Mass and Moments of Inertia. In this section, we're going to find the center of mass and moments of inertia of this thing called a planar lamina. And all this is just a 2D region. So it could be any shape, some weird shape, it could just be a triangle like this. To make things interesting, it's going to have variable surface density. All this means is it could have a different density at different places. So it could be more dense at the bottom here than it is at the top. So the first part, which this video will cover, is finding the mass of this planar lamina. And I'm just going to begin with a warm-up. So the warm-up is just evaluate this integral from 0 to 4, and then from 0 to y over 2 of 5x plus y dx dy. Okay, so here's the solution. We just work from the inside out. So the first step is just integrating the inside, and we get 5/2 x squared plus xy going from 0 to y over 2. Then we just plug in the bounds, so we get 5/2 times y over 2 squared plus y over 2 times y, and then the 0 term just is 0. So if we simplify that down, we'll get 5y squared over 8 plus y squared over 2 dy, which then becomes 9y squared over 8. Then we integrate this. So I'm going to pull out the 9/8, and we're going to have 1/3 y cubed from 0 to 4, which just becomes 9/8 times 1/3 times 64, which becomes 24. So the reason I had you do that warm-up is because that's how we're going to be finding mass. So I'm just going to give you the formal definition of mass of a planar lamina of variable density. So if rho is a continuous density function of the lamina corresponding to a plane region R, then the mass m of the lamina is given by m equals double integral over the region R of rho as a function of xy dA. So basically this is saying if you have some lamina, which I'm just going to draw as some shape, you want to cut it up into a bunch of dAs. So you'd probably pick one way and then cut the other way, and you'd have a ton of these tiny little squares, each with area dA. And this is basically at one point. So you would take dA and multiply it by the density at that point and basically add up all of these little masses for every point on the surface and then get the total mass. I want to point out this is incredibly similar to the equation we had in 13.2, where volume is the iterated integral with f of xy dA. The only difference is the letter. So instead of density, instead of having a z value at every point, you just have a density value at every point. And the process for solving it is basically the exact same as 13.2. Okay, on to example 1. Find the mass of the triangular lamina with vertices at 0, 0, 0, 4 and 2, 4. Given that the density at x, y is rho xy equals 5x plus y. So I'll give you a second to pause and try that. So the first step for most of these problems is simply to draw a picture so that we can visualize what we're finding the density of. So we have a vertex down at 0, 0, one up here at 0, 4, and one over here at around 2, 4, giving us this little triangle. And it might also be helpful to say that this line right here is y equals 2x, also can be written as x equals y over 2. Now we can write out just the simple definition to find the mass. And once again, we can go by either rows or columns, but we're just going to, for this example, show integrating by rows. So first of all, if we're integrating by rows, it needs to be dx dy, so that this inner thing can calculate the row, because we're going across x, across the row. Next, we need to figure out the bounds. So if we look at this row here, it just goes from 0, x equals 0, all the way over to this line, which would be x equals y over 2. So the bounds for the x integral will be 0 to y over 2. And then remember, we're adding up a bunch of these rows, so we're going to go from y equals 0 to 4. And then we're just going to substitute in our density function. And wow, this looks familiar. This is just the warm-up. And the reason I did the warm-up is because that's basically all you need to do once you set it up to evaluate it. So since we already did this, we know that it's equal to 24, and then it would be mass units. Now for example 2, find the mass of the lamina corresponding to the first quadrant portion of the circle x squared plus y squared equals 9, where the density at the point x, y is proportional to the distance between the point and the origin. So I wouldn't do this on your own because I'm going to teach new content with this example. So first, we're just going to draw a picture, of course. So we are only drawing the first quadrant because it's only the first quadrant portion of this circle. So it says the density is proportional to the distance between the point and the origin. This just means that really close to the origin, you're going to have very low density, and then as you get further away, it's going to be much more dense. And we can represent this proportionality basically with k, some constant that represents how it's proportional, the proportionality constant. And it's just going to be k times distance. Now, the distance is just going to be the square root of x squared plus y squared. That's just the distance formula. And now we can set up our integral. So let's integrate this by columns. So every column is going to start at y equals 0, of course, and then let's figure out what this top y is in terms of x. So let's solve for that. X squared plus y squared equals 9. So y squared equals 9 minus x squared, and y equals square root of 9 minus x squared. So it's going to go up to square root of 9 minus x squared. So if we create a double integral, then we can plug in the bounds. So we would go from 0 to square root of 9 minus x squared, then multiply by our density function. Since we're going by columns, it's going to be dy and then dx. And for our x bounds, we're going to go to x equals 3. You can see this is a circle with radius 3, so it's going to extend to x equals 3. And now we have this super nasty integral. So we have this really nasty integral, but we can solve this by, instead of using rectangular coordinates, using polar coordinates. So just how we were basically solving our previous things with the same method from 13.2, to use polar coordinates, we're basically doing the exact same method as in 13.3. So in polar coordinates, this distance from the origin to any point is just the radius. So we can say density is kr. Now, for our theta bounds, we can see that theta goes from theta equals 0 to theta equals pi over 2. And for our radius, we can see it goes from r equals 0 to r equals 3 everywhere because it's a circle. Now we just have to plug it into our double integral. I'm going to use dr d theta. And if you remember from 13.3, we're going to have an r here. And then we're going to plug in our density function, which is kr. Next, we'll plug in our bounds for radius from 0 to 3. And then finally, for theta, from 0 to pi over 2. Now all we need to do is just solve this, which shouldn't be too difficult. So first of all, we can write this as kr squared dr d theta. Then we can integrate the inside. So we get k over 3 r cubed going with bounds 0 to 3 d theta. If we plug that in, we will just get 27k over 3, which is also 9k. And since k is a constant, we can just pull this whole thing out. And while we're at it, we can take the integral from 0 to pi over 2 d theta, which would simply be theta from 0 to pi over 2, and we get our final mass of 27 pi k over 3, which is 9 pi k. And then I guess it would be mass units.